Freigabe. Not that one. That one. So you should see the screen now. Okay. And of course, the lecture will be recorded, and I will put it on YouTube, so that if for some reason you don't have time to come every time, you can watch it later, so that you don't miss anything. To write our C applications, we'll be using a software called Visual Studio. It's a Microsoft product. There is a free community edition available, so it's quite nice. Visual Studio. And it's not this one. There are like two Visual Studios. The real Visual Studio and this Visual Studio Code, which is quite not the right thing.
It's the same one that we used last semester, right?
Yeah, well, since this is like part one and we start new,
Yeah,
we
of
will
course.
install it from scratch. And in
Okay,
this
yeah.
case, the new version is 2026, but you can keep using the old version 2022. That is fine.
Okay.
They are similar enough.
Thanks, yeah.
Right. So here you of course select the free of charge community edition. There is one limitation that it will ask for a Microsoft account to be registered, but this is free, so you can create some disposable throwaway account just for this purpose. And during the setup process, you will need to select quite a few things correctly. One of the things I would recommend is to select always just English language, because if you try to search online for some issues or solutions, then if you are not looking in English, then usually your chances of finding some solution are significantly reduced. So it's quite useful to always try to work in English when doing things around programming. And what we need then, aside of the language, is of course which components we want to choose. There are quite a few, as you can see here, but we from this screen only need the C++ stuff. We can select for compatibility a compiler toolchain for the older Visual Studio, and quite a few other things just to have them, although that might work even without. So this is mostly the stuff that you need to.
Sorry,
Yes?
is Visual Studio accessible for Mac or only for Windows?
There is, I think, or there was some very cut down version that could work on Mac, but it's mostly a Windows application.
There's a Mac version, yes.
Yeah, so you can try
Okay.
downloading it. For the basic things we will be using it should be good enough. I guess you could even use Visual Studio Code, which is definitely available for Mac, but you will need to set it up for a Visual Studio, for C++, and I won't have time to show this here. So I only show you how to set up the normal Visual Studio, since it is the most feature-rich IDE available. Any other questions? Okay. So these are the things to select, and then you just press install, and this will now of course take forever. So that we don't need to wait, I already have baked a installed Visual Studio. We'll just quickly switch to the latest snapshot of my virtual machine, and then there it's already installed. You won't need any additional components, since this is a very basic course, let's say. We start at the beginning, so only in the part 2, which is next semester, you will need an additional framework. For here, just the Visual Studio is good enough. Almost. Needs to be slightly bigger. Yeah. Zack. Okay. So here it already has been installed. During the first start, it will ask you to provide a user account or continue without one, and to select a graphical style. So basically the initial layout of the sub windows. I just choose the general layout, and then once it starts every subsequent time, it shows such a start screen where you can either create a new project or open an already created project. So for us here, we can start by creating a new project. So it's most convenient to just use the normal. So we will just go here with create new project, and we can select which language. So of course we select C++, and we can select from quite a large selection of project types here. We could either start with an empty project, a console application, many others. There are some with a UI, like this MFC application. For us, the console application is the right one to choose, since it allows for an easy data input and output, since it has a console, so basically a text interface. and nothing other than that. The empty project would also be a good starting point, although there, if you want to use the text console, you need to change a few settings in the project properties. So after we selected what we want, we just press next, and then we can give it a name. So we'll call the project variables, since that will be the first thing we start with. And there is some here also the option whether we want there to be more or less directories created. So it shows you an example how this would look, but we will just keep it at the default. So we can go there to see what it will set up. A Visual Studio project is made up of a couple of files located in a folder. So created a folder, we have a solution file, and then we have here one project. If we add additional projects to our entire solution, then we would create more subdirectories with projects. The project as such is this VCX proj file with its associated additional files, and the source itself is the CPP file. And of course, as we add more sources to our project, we'll get more C, CPP, or H files than we see here. And the solution file just is like a shared metadata object that you can just open one thing and then have all the things needed for your application open. So if you would create some more complex project, you would, for example, have some executable file, and then you would have a library and maybe another library, or maybe a second executable file. And if those are dependent on each other in some way, so in case of the libraries, it's it might be a hard dependence, so that to build it really requires the other components to be present, not just during runtime. And here it is very convenient that you can have all of this bundled together. So when we go to our Visual Studio overview, we have here already the main source file open. It created some comments and some code already so that this thing is runnable as is. And here you can of course change properties of the whole solution, as well as properties of the individual projects. And so first let's just see what other toolbars we could add. So there are quite a few. I would usually suggest to add the build toolbar and maybe the debug toolbar, and this should be it. The rest is fine as is. So the Visual Studio is a so-called IDE, so an integrated development environment. This means it combines the functionality. There's a comment. Yes, there will be a recording and there will be a Moodle link put afterwards. A link to Moodle, a link to the recording put in Moodle afterwards. Also, I can send you already the download link for the Visual Studio in the chat. Okay, so where was I? Yeah. So a IDE, an integrated development environment, is a bundle of applications which are all needed to develop software. The most basic necessities is just some editor, of course, so that you can edit the actual source files, as you see here. Then you need a compiler toolchain, so a set of tools which can then translate this source code into an executable form. And then the nice to have things begin. So you would of course want to have a debugger, which is a tool which allows you to see what an application is doing, interrupt the execution, partially maybe even modify memory content, etc. So that you can easier find if something is misbehaving, where the error lies, why is it not working as it should, etc. And then in principle nowadays a debugger is really assumed as a absolute basic necessity, but for a long time this was like just a nice to have. So especially if you a few years ago still were playing around, for example, with Arduinos, most of them didn't had any debug functionality. The newer models do, but for the older ones you could write your application such that it writes some output to the serial port, and then you could, based on what the application tells you, try to find out why it is not doing what you want it to do. With a normal application on a desktop computer, this is in principle still a viable approach. You just write some sort of log output, and then if something stops working, then you see what it was doing last before it crashed. Or you can also program in some checks that if something happens that you don't expect it to happen, or rather don't want to happen, but expect that it might have happened, then if it happens, that it then writes you a log line, this thing happened, and so on. So this is how you can debug basically applications without having an actual debugger. But with an actual debugger, this is of course much more convenient, and we'll of course take a look into how to use it shortly. So obviously the first step will be to create an executable from our source code. This source code is very basic. It will just print on the screen the string hello world. How this printing works in detail we will take a look a bit later, since this is a lecture which should be suitable for people with no prior programming experience. We'll start very carefully at the very beginnings, but we'll also take a look on much more low-level things, so that the lecture should also be interesting for people that already have some or even have a good experience with C and C++. The interesting thing about C and C++ in comparison to many other programming languages is that it is very close to the hardware. So if you're using, for example, things like C# or Python, this operates at a much higher abstraction layer. Here with C and C++, you have more or less direct interactions with the CPU, what it is doing. So it is quite also interesting to see how the things that you program will then be converted into instructions for the
Sorry.
CPU. Yes?
What's the difference between C and C++?
C is a very small, well, first there was just C, and then they extended it a lot to create C++. So C is a language which is very simple. It does not know objects, at least no complex object. You can have a struct, which is basically just a piece of memory which you can inside the compiler structure in a way that it's easy for you to access individual variables and members of that thing, but the objects don't have any internal logic or any higher functionality. It is just basically a set of aliases for a piece of memory. C++ is an object-oriented language, so you can create objects, and in this sense an object is something that exists in memory, but the way it can, so basically like a struct, but the way you can interact with this object from your code is much more advanced. So an object can contain functions that will be executed on the object. The functions have automatic access to variables which have been defined on the object, so you don't need to for example, in C you could have a function, and then you pass your struct to the function and then some other arguments, and then it will do something with this struct using those arguments. In C++, if you define a function on an object, then you can just pass your arguments, and the function will implicitly know to which object it belongs to through the way how it is invoked. So in C++, the way you do it, you invoke either with the dot or with the arrow operator, depending on whether your object is located on the stack or allocated on the heap, and then you can call a function on that object, and internally it will know to which object to which member variables, to which piece of memory it belongs to. It is a layer of abstraction which makes programming much more convenient. But the interesting thing is that all the things that you do in C++, you could represent with C code. The code would be just much more convoluted and much less readable, and also much harder to write. Which is, by the way, a thing which we will do a bit later during the lecture. We will try to interact with complex C++ objects just from a C file, so without the compiler's help. And we will see that this, in fact, is quite easy to achieve. C++ then, of course, have been extended with a lot of helper objects. So the very first C++ was basically just C with objects. But since they had the functionality to create objects, they at some point created very advanced frameworks. So at the beginning, long time ago, the most common one was Microsoft founded classes, MFC. And later, the standard template library was created, which basically became a part of C++ and superseded MFC. So MFC was more like a Microsoft thing, which is external to it. So you have your C++ compiler, and then you can have the collection of these objects that you can use. And nowadays, the standard template library, which was created independently, basically became part of the C++ standard. So when you look on modern C variants like C11, C23, etc., a lot of things that are part of the standards are really improvements to actually just the STL, the libraries provided, and not to the language itself. There were, of course, things introduced in C++ much later, which are really new language features, like, for example, lambda functions. So that you can write a function within another function and pass it as argument to yet another function. So very nice things which people before that used in more abstract languages like JavaScript, for example. In C 98, such things were not possible, so we could not have local functions, etc. But those functionality was added. But as said, a very large portion of what makes up C++ is this template library. So we will be looking during our lecture into the most useful parts of this library. In the case that is open on screen, this std out is already part of the STL. So this is a subject for a bit later. It's important to notice that while the older versions of the standard template library really just were limited to some convenience functions and mostly container types, and working with the container types, etc., modern STL is pretty much a all-around framework. The only thing it doesn't do is graphical stuff, but you have all the I/O for the console. You have creating threads, thread synchronization, mutexes, etc. Anything you might imagine, reading, writing files, file system access. A great amount of things can be done through the STL nowadays. The older versions, as said, were much more limited, and for in just C, you had also a sort of standard library, but of course not object oriented, which also allowed you to do the very basic things like print things on a screen, read, write files, network sockets, etc. For graphical interface, you always need some sort of additional third-party library. In case of MFC, since it was from Microsoft and Microsoft made Windows, all these graphical things were part of this. But since the STL comes more from the rest of the world, they wanted to stay more agnostic, so they didn't add any graphical capabilities. On Windows and generally also on Linux, a very good framework for graphical stuff is Qt, which provides a insane amount of C++ classes which implement pretty much anything you might ever want with regard to graphical interfaces. And these classes, they are implemented in a way that is platform independent. So you can write your code in C++ using the Qt framework, and then you can compile it for Windows, for Linux, for Mac, and it will work. The Qt framework internally abstracts the platform-specific implementation. So the part that it exposes to you as the programmer is always the same, no matter for which platform you write. But on the backend, it has individual implementations for the different operating systems. Okay, any more questions? I see there is a question in the chat. There's a question about the attendance policy. So since the lecture will be recorded and available online, if you cannot come, then it is okay to just watch the recording, but attendance is encouraged at least. So it would not be ideal if you just not come at all. Mainly also because being here allows you to ask questions, etc. But if you need to miss 1 or 2 lectures for a good reason, then you can just do it. You don't need to come with an excuse letter or something like that. Okay, I see there is another comment in the chat. For Mac users about CLion, that is a IDE from JetBrains. People seem to like it. I don't have experience with it. Since it would be good if your project would be compilable with Visual Studio, I would recommend to try to get Visual Studio up and running. But if you cannot, or really doesn't want to, because Microsoft bad, the C files and C++ files, they are not dependent on like with what they are compiled. So as long as you are not using some Microsoft proprietary libraries, and as we said, you don't need to, since nowadays we have the STL plus the normal C runtime libraries. You could use this CLion IDE and then just upload the project, and I will figure out how to make it run on Visual Studio for evaluating whether it is working or not. So this is okay. Okay, then again a question about attendance. So as I said, I will just make a screenshot of the Teilnehmer window in Zoom and then check the attendance list manually. So you should have entered your full names into Zoom. I see there is one person without the full name yet, so I would recommend to correct this. Although if the name is not very common, I will manage to associate this either way. I did not mention that usually in the past, but since in the last lecture I had like 2 or 3 people with the same name, that started to be a bit confusing. So now I just ask anyone, at least for the first attendance, to enter the full name into Zoom, then the thing is easy. Okay, any other questions? Okay, no more questions, then let's continue. Right, so we were talking about IDEs and so on, and nice things to have, compiler, debug, etc. So another nice thing to have in addition to a proper debugger is a profiling tool. So nowadays, if you want to write code quickly, you might not necessarily write it very efficiently, and later on, if you not notice that your application is running slow, of course, the question is how you attack such a problem. One approach would, of course, be to just try to write efficient code from the get-go, but this might take much more time. So a reasonable approach is to just run a tool which will monitor the execution of your application, write down in which function your application spends most of its time, and then you can just directly review this data, and then you would explicitly only optimize those parts of your application which are actually timing critical. So this is something that long time ago one would of course frown upon, because long time ago CPU resources and RAM was very precious and very limited. Nowadays they are more or less available in insane quantities in relation, so it's more efficient to save your time and then really only optimize the hot paths where your application is spending most of its time, while like things which are just called a few times per second and not use much, not end up using much CPU time, can be left technically unoptimized. Visual Studio, for example, has such a profiler tool, which is quite nice. I don't know about CLion or the other IDEs. I would imagine they should have such functionality. Yeah, so let's continue here with our Visual Studio. So we wanted to convert our application into a executable. So in Visual Studio it is particularly easy. There is this local debugger button, which when you press, it will compile whatever is needed to run the project. In this case, it's of course quite trivial since we only have one project. And the compilation is made up of 2 steps. So first of all, we see that this worked. So that when we switch here to the build log, we see that there are 2 things. At least it should show us 2 things. So one is that it actually compiles this CPP file into a object file, an intermediate representation. So we see here that it added this x64 directory and that subdirectory debug and created our executable and our PDB file. So first things first. So obviously the executable is our executable. The PDB file is a debug database. So inside an application, all the function names, variable names, except for certain exceptions, if you export symbols like in DLLs, are not persisted. So a function basically just starts at an offset, then has its content, and then ends without any markers that would really say this is now a function and the function ends there. You can, of course, from analyzing the binary data, deduce that this will be a function. It probably starts here. Here it looks like it's the last return. So, well, you can reverse engineer things, but obviously this is quite not what one would want when debugging one's own code. So this is what this debug database is for. It contains pretty much all the necessary information how the compiled version of the application relates to your actual source code. So for example, it has a list of all the functions and the offsets within the executable file where these functions start, how long they are, for variable names, in which registers, in which memory regions, which variables have been located, etc. All those things that the compiler does for you to convert your human readable code into a representation that the CPU can understand. The relevant steps are saved in this debug database, allowing you to or rather allowing the debugger to show you quickly and easily much more relevant information when you are debugging the application. We will be debugging it shortly, but let's see what other files have been created. So when we go into the project, we have another 64 folder, again with debug and with quite a few more files. So those are, while the other files we have seen is more or less the final product that you want to have is your binary and a PDB file which you might want to keep in case you want to debug it later. But it creates a large amount of intermediate files which are really only important while building. It doesn't delete them instantly, because if you just change one file in your project, then of course you don't want to recompile everything each time. To save time, it will just update the files that changed, and then from those files create this final representation. So here we see that we have one variable object. This is created from the CPP file. It is for the most part already compiled, but the code as is position independent, so it has no linking to any other components it would depend on. So it's like it's a raw piece, and then a lot of these object files need to be assembled together, connected together. This is called linking, and this is the process which then generates the final exe or DLL or other sort of executable, as well as the debug database. Some old versions of compilers also created other intermediate files, which were quite even more illustrative about how C and C++ actually works, but for our purpose this is not really interesting and we will not be looking into that too much. Generally, just as a note here, if you are uploading homework for Visual Studio, then of course you would want this and this, but not this, and you don't need to upload the binaries. I will be compiling it for the grading myself. This .vs folder is also not needed. This is again a different thing. This is created by Visual Studio and contains metadata related more to the graphical experience and the configurations here, rather than to actually compiling things. So if you would be compiling the project from the command line, this folder would not even exist. In Visual Studio, there is a command line tool that allows you to build projects fully from the command line, which for automated workflows is quite useful. But we won't be using this since we are more on the graphical side of things. Okay, so we have compiled an application as we have seen it already ran. So the next thing we can of course see is how this so-called debugging works. Generally, there are two ways how the debugger can be invoked. One is that you just, well, technically 3 ways. One is that you just invoke it actively. When the application is running, you will have additional buttons which allow you to interrupt its execution. This way of debugging is kind of not particularly useful because you're just breaking into the execution wherever it's right now. It's very untargeted. It can be useful if you are caught in some execution which just repeats the same code over and over and never ends, then you will be where you want to be. But normally you would want to use one of the other ways of the invoking a debugger. One is that if something happens inside your application which causes an exception, exception meaning that the CPU tries to do something and then realizes that this is not a valid operation, it will internally trigger an exception which then the operating system will handle, and this will either cause your application to crash, or if a debugger is attached, the operating system will instead tell the debugger the application ran into an exception, here are the details, do something with it, and then the debugger will show you as many informations as it reasonably can at this point, where the error happened, what are the local variable values, etc., etc. But of course, this way of debugging is you need to wait for something bad to happen. It is much more targeted, but still, of course, not quite satisfying. So we have a third way, which is the most convenient. This is through the use of so-called breakpoints. So what we can do is you can tell the debugger that when your application starts executing code which corresponds with a particular line of your source code, then the application should stop and the debugger will be shown to you. Internally, how this is implemented is quite interesting, but that might be a bit too advanced to just describe it now. So we will just, on an experimental level, see how it behaves. So in Visual Studio, the simplest way is you just click here on this bar. You can also toggle it with F9. And in pretty much any other IDE, the way this graphical debugging is implemented is this way. You are just clicking next to where you want a breakpoint, and then once the application executes to a point where this breakpoint is reached, it breaks, as the name suggests, and then you can inspect what is happening. And the great thing about breakpoints is that you can resume from them. So basically, we can try it. So we press play. Now what happened is our application started, so actually it is running right now, but it has been suspended, so the code is not longer being executed. And here we see this yellow arrow indicating where the thing is, and we can, once we would have some variables, we could see their values here in locals and so on. So we will look into this in a second. And the nice thing is that when you press continue, it will just continue. If you would have ended up in an exception, if you press continue, it will just retry the same exception and give you the same error again. So there kind of is no way to continue from an exception, at least not an easy way. You could, of course, try to edit the memory from the debugger, but this is something that usually you are not doing. That is not usually a useful approach. Now what else do we see here? So here we have, of course, a list of breakpoints, so we can have many. We could also disable a breakpoint without actually fully removing it. What also can be set is when you have a breakpoint, you can go on settings and then you can create a condition. So you could specify an equation using the local variables available to you at this point. And only if this condition is met, then the breakpoint would trigger. this is, one should be a bit careful using this functionality, because the way this is implemented is that the breakpoint always triggers, then the debugger evaluates the equation, and then it just tells on its own the program to continue, or rather it tells the operating system to make the program continue. And this is quite a slow process. So it's if you have a code which is running in a loop, so it repeats itself for a large amount of repetitions. Having such a breakpoint with a condition inside might be quite inefficient. So just this as a small caution. Then of course here we have something which is very important, but we will be learning how this works in more detail in one of the later lectures. It is the call stack. So I guess this is a good point to touch on how a program generally is structured. So on the lowest level, so since this is a low level lecture, so this is I guess a good place to start. Any program is just a very, very, very long list of instructions which the CPU is executing. So basically it reads an instruction at some entry point offset where it starts. It executes the instruction, it proceeds to the next instruction, and so on. And then at some point it has an instruction that tells it to terminate the execution of the program. And programs usually are structured in functions. So you would not want to, you could of course write a program like one extremely long function and nothing else, but this would be of course quite not easy to handle. So pretty much any reasonable programs or programs of non-trivial complexity are made up of multiple functions. A function, you could also think of it like a subroutine. Is characterized by this, that you can so you have your code, you have your executions, you are doing something, and then you can issue an instruction which will make the CPU jump to a function, and then the function will do something, and at some point from the function you can return to the exact point from where you started, and then continue doing other things. And this you can of course do as often as you want. You can call a function from a function, and then call other functions, etc. So this is only limited by your hardware resources, how much functions you can have called one after the other before something crashes. And this call stack here is such a representation of functions. So it shows you the function which you are right now, and further down it would show you the functions which have called your function, and then the function that called the function that called your function, and the function that called the function that which called the function that called your function, and so on. Here, as Visual Studio by default is configured, we only see functions in our own code, and then we see this external code, which for many applications is good enough. You are usually not interested in seeing what's happening in the guts of some Windows DLLs, but for our applications we of course want to see it. So when you right click here, you can select show external code, and then you will see actually how this looks. So we have our main function, then we have another which and maybe a short note how the display here is structured. So we see the name of the module, basically which executable or which binary image the function is located in. Then we see the name of the function, then it even tells us the line number if it knows it. And we, for example, one thing we can notice here is that while our application only has this one main function currently, there seems to be a second function called invoke main, which we don't see, we have not created it. It was created for us by the C runtime. So when we double click on it, we can even jump to its source code, which is located somewhere, as you can see on this tooltip, inside the Visual Studio C runtime provided files. And this basically will be compiled as part of our project, even though it is not something that we have created here. And then there are even a few more such functions created and executed already before our main function was invoked. And then we see that the first entry point of our binary is then invoked from something from the kernel 32 DLL, which then again is invoked from something from the NT DLL. So these are parts of Windows, and every application starts its execution inside the NT DLL. Basically, there is an entry point in the NT DLL which gets executed, and then it starts setting up things, and only once most of the when all of the necessary things have been set up, only then it invokes the entry point. Windows invokes the entry point of our application, which sets up other things which are part of the C runtime. I will talk about the C runtime in more detail later. And then only once everything has been set up, our actual main function gets called. If you want, and here, for example, you see that while it shows you the name of the module, like NTDL or kernel DLL, it doesn't show you the function name. It just shows you a strange number, basically the memory address. And we can, in fact, get this information. We can, where was it? Microsoft is providing symbols for these modules, and we can just select here either load symbols that will only apply for the one module, or we could select always load, so always load automatically. Then it will, whenever we encounter anything that is not yet loaded, try to load it from the Microsoft server. So here, let's do it manually. So this will only work for the one file. This might take a second or two, and for the other file as well. Zack. And now we have the complete list. So we have now RTL user thread start and base thread init trunk in these two functions. So we know more or less where our execution comes from. Of course, knowing what Windows is doing is not necessarily very useful if you just want to debug your own application, but you can, I'm sure, imagine now that once you have an application with multiple functions that are calling each other, and you put a breakpoint in some function, then it will be very important to you to see which other function called it and what happened before. So these things you can navigate through with this call stack. There is also another nice window called immediate window. Here you could write simple equations like to get a value of a variable, or calculate something like if you want to know to which memory address adding something to a variable evaluates, etc. You can do it here. On this locals, this we will try shortly. What you see here will be variable names of local variables, but we don't have any, so we don't see anything here, but that will come. And there are a few more nice windows you could open when you go on the debug and then Windows. Then you have a whole list. One is the registers that will be relevant very soon. How can I grab this? Like this. The new style of the Visual Studio is a little bit. They changed it a lot. So the old Visual Studio looked much more classic. This is quite modern. So since not everything looks as expected, I might need a bit more time to find myself. So we have registers. What this is, I will tell you shortly. Then of course memory, which allows you to read the memory of your application. I will tell shortly more about it. And then last interesting one is the disassembly. Let's put it here. So as I said, and I'm sure you knew, at least assumed, the source code that we have in C as such is not directly executable, so this needs to be transformed into something that the computer understands. As I already mentioned, this is called compiling, and the code that is generated that ends up in our exe file or DLL, etc., we can actually view this entire code here in the disassembly window. Technically, we just see the code for whatever we are looking right now, so it's not disassembling the whole thing again, but it just does this like in small portions. If we want to see something, we can see it. So in this case, it shows us the source code because it's aware of it. So if we go back to our call stack to main, then it shows us our source code. Then it shows some CPU instructions that it has generated, then some more instructions, etc. We will be taking a look into those in detail a bit later. And we can select what we want to see. So of course, we see the source code. We could disable it if we are not interested in the source code. Then it will just tell us the function names. You can set it so that it doesn't only show you the assembler name of the instruction, but also the actual bytes that have been written to the binary file. So this is maybe something I should also mention in a little bit detail. So the machine code that is executed by the CPU, while it's of course some sequence of bytes that has a meaning, it always is translatable one-to-one into so-called assembler instructions. So the idea about assembler is that you really have a one-to-one mapping between what you have in your binary and what the assembler is doing. Of course, modern assemblers have quite a few convenience features which allow you to structure the code before compiling data that kind of get lost if you just compile it and then disassemble again. But unlike with C++, when you have something that you have written in assembler, you can really decompile it, and you basically have back what you started with without some convenience features. With C++, they are of course modern decompilers that can take a binary, disassemble it to the assembler instructions, and then try from the assembler instructions to guesstimate what C or C++ code probably was there, and how this looked. So there are such things. They are not part of Visual Studio. There is one open source alternative, actually two, which are quite good, x86DBG and Githra. And then there are commercial options for this. One is from Hexrace called IDA, and another one is from it's called Binary Ninja from, I don't remember how the company is called. But if you Google for Binary Ninja, you will find it as well. Usually the commercial versions are very, very expensive, so the free versions are much more user-friendly. Anyhow, the important thing is simply to know that that basically the way how C++ kind of operates and C operates is it can, in the old compilers you could even get the intermediate code given out. So if you have any sort of C file, C++ source file, this can be compiled into just assembly instructions, and then these assembly instructions can be compiled into the actual binary instructions that you have inside your executable file. Modern compilers don't really show you this intermediate step, but they basically just execute it in one go. But the very old compilers had options that you could, for example, keep the generated assembly files, etc. Nowadays, if you want to compile something to assembly from C++, you would rather just compile it and then disassemble it and get your assembly this way. Okay, so this is this. I think for the debugger we have taken a look already on most of the important features. The other things we will learn in learning by doing, so to say. So let's stop this and let's start at the beginnings. So obviously, since we are starting with the very basics, the first things will be rather simple. So just be patient. The interesting things will start soon enough. So the most basic thing I think one can imagine with regard to an application is that you need somehow to store your data, and as I'm sure you already know, since nowadays most people already had at least some experience with some sort of programming, you do this using variables. So you can define in your program code, like in mathematics, just variables and assign values to them. The difference to mathematics is that in mathematics any variable can more or less be anything, like in JavaScript, while in C++, which is a strongly typed language, a variable must be defined. You first need to tell which type of data will be stored in the variable, and then you can only store this exact data. There are some ways how you can cheat around this. So if you have a variable of a larger type, you can put smaller data into it, etc. But this will not change the type of the variable. It will just somehow shoehorn your data into it. So let's start at the start. And of course, one more important thing before we maybe even talk about variables are comments. As you can see here, that there is this green text, which seems very much human readable, and that's on purpose. A comment is basically a piece of source code which the compiler completely ignores. It's only here for humans and nowadays for AIs to help them to understand what the code is doing. Because if you write some elegant code which is self-explanatory, that's fine. But sometimes if you want to do some particularly efficient, performant things, you might do it in a way that if you look on the code, you see just what the fuck is this doing? It might be technically it's self-describing, but it may be self-describing to a machine, but not really self-describing to a human being. So this is what comments are for. Also to explain other things. For example, if you write a function which is a few pages of text long and has a few arguments, then you can of course give names to the arguments. You should give names to the arguments, not call them just argument 1 through n. That would be very not user friendly. But if you say like an argument is called, let's say, flags, what does this mean? What flags? That's not self-describing. So that is what we are using comments for. You can just write this additional text which the compiler will ignore, and then really in your normal human language, whatever language you want. I would of course recommend English, since this will be most user-friendly to other people that will later read your code, but you can also write in some invented language that only you understand, and it will be perfectly fine. And in C and C++, there are two types of comments that you can have. You can have a single line comment, as we have seen already here. Basically, you have code, and then you make two forward slashes, and then you, after those two forward slashes, unless there is of course something in between, so if they need to be one after the other, everything after it until the line ends is just a comment. And this is for many applications already good enough, but there might be situations where you want to, for example, disable some piece of code inside a line of code, and one option of course is you just make a copy and keep the original as a comment, but the other way to make a comment is to use such so slash asterisk and then everything including new lines and line breaks, everything between will be treated as a comment. So on one hand, it is quite easy, quite nice if you want to write a larger block of text, then you don't need to prefix everything with backslash. Although nowadays, the IDE, the editor, just does this for you. But of course, the old IDEs in the last millennium, I didn't do such nice things. So there, you would need to do it by hand, and it would be annoying. So just creating a multi-line comment. This thing even gives you asterisks, which you don't really need. It just this because people like to do this because this looks nice. It is really just all convenience nowadays. But anyhow, if you have larger portions, then you can comment it out this way, and you can use this method to I already used the term without explaining it, to comment out something. Basically, you have some code, and then you want to see what your application does if this code wouldn't be here. You can of course delete it, but then if you delete it and you want it back, what do? You save it to other file. That gets complicated. So you keep it in the clipboard, and then a PC crashes and the clipboard is gone. Also not great. So what you do is just you put such two multi-line comment markers around your code block. And unless your code block already contains some multi-line comment, because that then breaks it, of course, since it doesn't count like this one and the second one. Like, I mean, it ignores the second one, but if I put the end here, it already complains that this is no longer part of the multi-line comment. So you cannot comment out code blocks. Right. So it is not possible to comment out code blocks which contain multi-line comments this way. But another thing what you can do is Visual Studio, what was this? Control KC. Was it? Or was it like this? Control KC. Yeah. And KO. So there are key combinations which allow you to just comment out with single line comments whatever large code block you might want to comment out. Where was that? Advanced. We can also make things uppercase. Do I see it? Can't see it. Somewhere it is. Advanced. well, you can here comment section, uncomment section, KC. So basically hold down Control, then press K, and then press while you keep Control pressed C, and then or U for uncommenting it. So they're quite it's quite useful. Okay, but I guess we already said what comments are, so let's return to our variables. So since as I mentioned, the variable need to have a type, then of course the first thing is we specify a type, for example a char, and then after the type we give the variable a name. Let's say my char, and in C++ any expression is to be terminated with a semicolon, which is quite different to many other programming languages. And if you are coming from another programming language, you will probably often forget to make the terminating semicolons, and the compiler will complain. But that's why it is here. So this is, by the way, something we haven't seen yet before. If we just write invalid code and then try to compile it, what it will do is it will just tell us that it failed, and it will generate basically two outputs. One is the text output, which is generated by the toolchain itself, and from reading this output, the IDE creates such a nice list of what's wrong. And here it says it's expecting a semicolon, and that the closing bracket here was unexpected because the semicolon was missing. So if we fix it, it is happy. Now of course we could run it. It will not do anything except running into a breakpoint, obviously. But what else you can do? So basically in C++, you can use equations a lot. So of course you can just assign a value. You could also write already here some equation, but we will do equations and operators a bit later. So for now, let's continue as is. So, and usually, of course, this is an important difference between C/C++ and many other languages. In C and C++, if you create a variable, the variable will not have a defined value. But unlike, for example, JavaScript, where an undefined is, in technical terms, a somehow defined state. It is defined to be undefined, basically. In C++, if a variable is undefined, means it will just contain whatever memory garbage was in the place for which it was reserved before it was set up. So basically, you will just get garbage from whatever was before. And this is quite dangerous because such a garbage might often be zeros, which might be what you expect. And then sometimes it won't work because somehow there is a strange value there. So it is important to initialize variables before use. In the sense before you use that before you read from them. You don't need to initialize them once you define them instantly. If you know that the first thing you will do with the variable before you read from it, you will write to it. Then you can skip this and you will save some very small amount of CPU time. But if you are sure that you will always write to it first, then you can skip it and then just write to it. Given that it is a very small amount of CPU time and that such a bug can be very hard to track down, I would always recommend to initialize all of your variables instantly, because then you start with a defined state. And at this point, before we continue to other variable types and so on, I would maybe put in a very small detour. So the compiler, which we are using here, like many others, when it creates a binary file, it usually can do it in a few different ways. So you have presets. In this case here, for example, you have debug and release. You can define your own presets. Those presets basically are just a collection of properties. So you click here on properties and you have here all this really long list of options, and then you have more options, and then you have even more options, and so on. And a collection of all these options can be basically set here as a configuration, as a preset, either debug, release. In this case, we could add any other, like alpha, beta for testers, etc., whatever. And then we of course have a platform. So this is something I will explain in detail in a second. but the idea is that with this debug and release, that when you are debugging when developing an application, you would select this debug option, and then the compiler will add a lot of safeguards to your code, which will be made for your code to, if something bad happens, to crash here and there and here and then, and show you what happened when it happened. If you, however, select release, it won't do that. You can manually, of course, enable various additional safeguards, but like the most expensive safeguards will not be applied because they really would slow down your application. So you might find yourself in a situation where you have something as a debug build and it seems to behave because there is some initialization which so if you have a debug build, usually any uninitialized variable, we can, by the way, try this out. Put a breakpoint here. Let's to 0. Oops. A breakpoint. I forgot the breakpoint. Okay, and then we have here our locals. So we have our char. And currently it looks like it contains just 0. But if this would be a release build, then it would not necessarily be defined what it will contain. The problem with testing such a simple code in release builds is that what the compiler does for release builds is it optimizes the code a lot. So if we have just a variable which doesn't do anything, it will end up entirely removed. So it's not so easy to play with that. And one more thing to be said here is that there are quite many configurations which for our purpose later might be a bit more through generation of much more extra code will just not be super great. So we will later on the code generation disable a few of those things. But I just wanted to tell you that this initialization behavior of variables very much will depend on the configuration that you have selected. So you should expect that this might change, and that therefore ideally you should just always initialize it with a known value. This avoids really a lot of potential mistakes further down the line. So coming back to our variables and our char. So char sounds like a character, and it is. It represents 1 byte, so 8 bits of memory. It always represents 8 bits of memory in modern systems. There were some extremely exotic systems where you might have a different char lengths, but pretty much anything made in this millennium will be using 8 bytes as a 8 bits as a basic unit. And such a char basically is a number, so it's an integer number, 1 byte, and it can hold values between -128 and 127 plus. Interestingly, integers can hold one more negative value than positive values. This is related to how the numbers are represented, on which we will take a look at shortly. And these numbers are integers only, so they don't have any comma, any floating points, and anything. Modern computers can handle floating point numbers just fine, but they use a different data type for it, or rather a set of different data types. Very old computers, like again from the last millennium, the first ones really just handled integer numbers, and if you wanted to do anything with a floating point number, you needed an physical extra processor that you put on your mainboard, which provided a floating point unit that was able to handle floating point numbers. Okay, so let's see. So we have here our 1 byte. What else do we have? We can have 2 bytes, which is called a short. My short. We also give it the value 0. At this point, maybe another small detour. You might notice when I'm talking about things, I'm sometimes going on tangents. That's unavoidable. And the tangent here will be about how to name your variables or functions. Basically, in C and C++, you can use letters, small and large, underscore, and numbers. the names are case sensitive. So if you call something my char and my char, these are not the same. For a human, they are the same mostly, but they are not. And this is kind of important to know that there is this distinction. Since in C++ any variable needs to be defined, this is not that much of an issue. Because, for example, in JavaScript, which also makes a difference between capital and non-capital letters, if you define your variable as lowercase and use it and then write it with an uppercase letter, for the compiler it will look like, oh, a new variable is used. It's probably a 0, so I will just use undefined. And it will not even complain. C or C++ code will not even compile. It will just bug out unknown variable used, and then you have to correct it, which is good. So generally, for programs working correctly and not crashing, the more strict a language is, the better. It is also, of course, at some point more work if it wants everything to be very strict. So like the very modern languages like Rust, for example, I think they are more pain in the ass to work with than what it's worth. But on the other hand, they offer really superior memory safety guarantees. So it depends on your use case what you want to use. But I said in C++, it needs to be defined and it's case sensitive. Another thing to know is while you can use numbers, you cannot start with a number. So the first character of your function or variable name must be a letter or underscore. Underscore is also fine, but it cannot be a number. And after the first letter, you can use whatever you want with the mentioned character set. And another thing to mention here about naming is you cannot use a space, obviously, since spaces are separating things. So if you use a space somewhere, the thing will complain. So if you want to give a name to your variable which in some way is made up of multiple words, how do you do that? Well, one option you already see here on screen. You just use underscore in place of a space, and that's it. The other option is that you just capitalize whenever you want to switch from one letter, from one word to the next. You can also capitalize the first letter, etc. Which one do you use is pretty much up to you. It doesn't the compiler doesn't care. And I'm sure about which version is more human readable. There will be a lot of studies and they will all disagree. It's really probably mostly to what you got used to using, and this is then the best for you. This sort of writing is called snake case because everything is lowercase, like it's scrolling around on the floor. While when you are using capital letters, it's called camel case. I guess because someone thought it resembles a camel with its legs when large letters are standing out somewhere. And what else about the naming? Yeah, and one more, I think. In old school, very old school programming languages, where you didn't have like types explicitly defined like here, what people often, what was necessary was, for example, that you had to use a certain letter prefix for your variable to indicate which type it will be, which is obviously quite not very user-friendly, since in C you have defined explicit types, much better. But people used to add prefixes to their variables. So, for example, a char would be like C char and S short, something like this. So to indicate, if you read somewhere a variable name further down in the code where you don't see the definition, that you can see already on the name which type the variable is, which seems useful. Nowadays, this is not really necessary because as soon as you move your mouse pointer over it, the IDE, if it's any good, will look up the variable where it is defined and tell you exactly what do you have here. So which type, is it local or global or in an object scope, etc. So using prefixed letters is pretty much a very quaint way of naming your variables. Of course, if you want, you can do it. I would recommend to use the P prefix for pointers. What pointers are, we will learn later. but the other prefixes I don't think are really useful. Plus, like S for short and S for string, and that's already confusing. So for string you would use str, and then you have already more letters. So um, nowadays just use P for pointers because it's important to know that something is a pointer. But for the other types, it's not so critical, and the compiler, if you misuse it, will complain anyways. So let's go back to our initial writing style. Okay, so that was this tangent. So let's continue with our short. As I said before, a short is 2 bytes, and it can of course represent already a much larger span of values, from minus 32,768 to let's make it like this. Basically the same number plus 1. Sorry, minus 1 and positive 7. Oops. 767. So this is already much bigger. So basically this can in total represent about 64,000 values. The next bigger type is a long, which is defined as 32 bits, so 4 bytes. My long is equal to 0. So maybe align it. So it's always good for readability to maybe align your code with some tabs so that it's easier to read. So 4 bytes, and this is an even bigger number. So for minus 2,147,483,648 to the same number, just one less, and positive 7. Also a note with regard to floating point numbers, which we'll take a look in a minute. In C++ you use dot for the comma separator always, not the comma. Right. So it's obviously much bigger. Often you will find 32-bit variables also called an integer, int. And in fact, there are quite a few aliases for those different data types, which I will show you in a second. But of course, one thing we certainly are interested in are 64-bit numbers, since I guess most of you know that modern CPUs are all 64-bit. You still can find 32-bit CPUs in embedded platforms, in microcontrollers, etc. But pretty much any computer, any smartphone, any more advanced computing device you can buy nowadays will use a 64-bit CPU. So 8 characters long, and the type in here is int64. So it's a 64-bit integer with 2 underscores. The name is not particularly nice, but that's how they defined it. One of the reasons, of course, is that the old compilers never supported 64-bit, and then this was added at some later point, so they wanted to ensure that this will be collision-free as possible. My int64 0. Now we see I have not picked enough tabs for a nice alignment, so let's quickly fix this. Oops, and these are 8 bits, and the number is very, very, very large. I will just paste it here and not try to type it by hand because this is too error prone, and so I noticed we need more space here as well. Oops, 2, 7. So this is a pretty big number, and as I said, there are various aliases that you can use as part of the language directly. So for short you would also write short int. For a long you could just call it an int, although there is a important catch with that, or long int. Long int is fine, just int is dangerous because int just means integer, and it does not technically tell you, like within what this language is concerned, how many bits or bytes does this integer has. So it will be platform dependent. So if you write something in Visual Studio for a Windows target, it will always be 32-bit. Interestingly, even on a 64-bit system. While if you would compile something for an Arduino, for a very small Arduino, while it's just an 8-bit CPU, it would default integer to be a 16 bit, so 2-byte long integer. And in principle, one could expect that on a 64-bit platform other than x86, you might find int meaning a 64-bit integer, but in practice, this is not something you will encounter. In practice, 64-bit integers are almost always explicitly marked as 64-bit, and the normal integer just goes up to 32-bit. You will also, I guess, not find in the world any still useful compiler that would interpret an integer as just 8-bit, so one char. The major disparity will be just, is it 16 or 32-bit? On Windows, it is always 32-bit, but as I said, if you have some code which you wrote for Windows and then you want to use it on an Arduino, you might run into issues that your integer is different. The other names like long or long int are fixed. They will so a long int is 32-bit on the Arduino, on a Windows PC, or on anything else. So it is fixed, and if you want a nicer name for a int64, you can use long, which again is kind of weird because kind of you have long int, but a long sounds really different. But this is a valid name, and I said this. The reason why this was introduced in such a way was that when the 64-bit compilers have been introduced, people wanted to ensure that you can take a 32-bit code, compile it on a 64-bit compiler, and it should be mostly working, ideally fully working, that you then really where you need 64-bit and explicitly add it. So there was something on the chat. Right, so this is not relevant for here, so let's say this is yes. We have these aliases names, and the next thing of course we can have, so here with all those types, one thing we notice is that they contain positive and negative values, but in computing you might sometimes be interested only in positive values. So for all these types that we have here, we also have a variant which does not contain negative values. It's called an unsigned unsigned, and then you just use the same types that we already have, like char, etc. So my char. The prefix u is of course quite convenient to indicate that something is unsigned. Let's move those things a bit more to align. And we can use a different notation if we want this time. 0. So this now contains values from, so it's of course still 1 byte, but contains values 0 to 255, which is in hex 0xFF. So the hexadecimal notation is something you will also encounter a lot of in computing. There are also two more notations to which we will take a look at shortly. But now let's continue with this short short 0x0000, and already one note about the hexadecimal notation. As you see here, we actually specifying the right amount of zeros to fill in the whole variable. We don't need to, we could just write this. That would be fine, but it is nice to do it like this because then we directly see how large the value is that we are writing there. So the hexadecimal notation splits any binary number into 4-bit nibbles, and they are really called like this. A 4-bit unit is a nibble, and this is a value between 0 and f, and this maps 1-to-1 onto what you would store in your memory. While decimal numbers are somewhat ugly in this sense. They because like for example here it can be 128, but it cannot be 129 anymore, even though it has the same amount of places, so it doesn't map nicely, while the hexadecimal notation maps perfectly bit aligned with this nibble notation. Okay, so this is 2 byte, 0 to 65,535 0 XFFFF, and you can of course use also lowercase or uppercase. Both are fine. They don't have a meaning. They just one looks nicer than the other, and you can choose whatever you prefer. Okay, then we of course have unsigned long. Long my u long 0x 1 2 3 4 5 6 7 8. So that's already a bit longer. Visual Studio is here trying to align, to auto format whenever you press a semicolon or close brackets, then it will auto format to whatever it wants, and unfortunately it does not like this nice formatting. So if we allow it to auto format, we end up with something like this, which is ugly. So let's keep it manually formatted for Butes. Again, from 0 to 4,294,297,295. 0x 1 2 3 4 5 7 8, and of course our integer, 64-bit integer in 64. My u in 64 is equals 0x and it's barely enough, 8 bytes, 0 to very large number. Right, and what you can do is, if you want to ensure that the compiler knows, I know it's not enough space, which type of number your literal should take, then you can add a suffix. You can add ul, unsigned long, and ull, unsigned long, and this tells the compiler that it really knows what it is supposed to be. In case if you're of course using a hex number and provide so many zeros, then it will know this implicitly. But if you would just use a hexadecimal number, sorry, a decimal number instead of hexadecimal number, then it would not necessarily know this. Let's say if you take the number 5, it will not know how many bits you want it to have. So then you could use these suffixes to specify this explicitly. L, and the other ones is just L and LL. Okay. Any questions so far? The chat, here's the chat. Okay, then I have a question to you. So the lecture is written up from 3 o'clock until 7:30, until 5:30, 17:30. But this is like 15 minutes longer than 3 academical hours. So we have 2 options. Either we will have a 15-minute break during the lecture. I mean, we had also in between option that we make like a few shorter breaks, or we just finish 15 minutes early. What is your preference on that?
Let's blast through. That's my opinion.
Okay. Fine. Then let's continue. Okay, so right, so we know what variables are. So as I mentioned, there are also floating point numbers. So these were integer variables, and the other type of variables are floating point numbers, which, as mentioned, modern CPUs can execute directly without any additional help. And there are only 2 types of those: float, my float is short for floating point, basically 0.0f. As mentioned, use the dot to delimitate the comma, and f to indicate that this is a float, and the float is a 4 byte, i.e. 32-bit number, which can be plus or minus 1.17549 e plus / minus 38. So you can already represent quite a large value range with a float. And if you are writing a computer game or something that does not need huge precision, you would go with floats. If you're writing AI, you would even want less precision. Apparently there are nowadays floats down to even just 4-bit used, which is crazy, but apparently it works. So well, whatever works, I guess. But the modern typical CPU can only handle 32 and 64-bit float numbers. As such, it cannot handle those shortened types that are used in AI training. And for any sort of scientific calculations where you want precision, especially with regard to error propagation, you would use a double or a double precision float, but it's just as the name double, my double, and it's written just like a float, just without the f. So there is no like d or something, and it's 8 byte, i.e. 64-bit numbers, and this can handle, what can it handle? Much more here, and here is 2.22507. So the range is much greater, the precision is much greater. So if you run a lot of calculations and with a lot of intermediate results, some error will accumulate, but it probably will be negligible. With floats, this really is not the case. If you try to compute something more complex with a few more steps and a few more intermediate values, you might run into rounding errors very quickly. An important thing to know is that you should only use floats if you really want to do something well that needs floating point numbers, because of this error behavior. Interestingly enough, the specification for floating point numbers is not such strict that you will on every platform, if you do the same operation, get exactly the same result, because a lot of operations with floating point numbers, like taking a square root or a sine function or something, they are not just simple operations, but they are basically based on executing some algorithm for a certain amount of iterations, and the longer you run it, the more mathematically precise your result will be. But of course, then you would have everything would be very slow. So they are in the standard set definitions which level of precision you need to have, and different hardware vendors might in fact even choose to run those algorithms longer or shorter inside their silicon, so that you might get different results with regard to the very last comma places, depending on where you are running your floating point code. So if you are working with things that need exact numbers, use always integers. As you have seen here, they are limited to a certain range of values. So you might have a use case where you need bigger integers, like for example 128-bit or 4 kilobit. This often is used in encryption. So RSA uses key lengths up to 4 kilobit or even more. 4 kilobit is basically what you would consider secure by today's standards, but not necessarily by tomorrow's standards. Or different other encryption methods, they all will use rather large integers, and the CPU, at least with its basic command set, cannot handle such numbers. So what you would do there is you would write your own implementation, some own code, which breaks the number up into smaller pieces and then implements in software support for large integers, basically as big as you might might want to use them, either as a fixed length, so for example a fixed 128-bit integer, or as something that can have any length when you define it. In the second part of this lecture, so in the next semester, we will in fact write such a class, a C big int class that can represent numbers of arbitrary size until your memory is full. Okay, but here we will be only really looking on those very basic types that the CPU can handle itself. There are also other types that are defined than those that we have seen here, but they are defined to be used with special CPU extensions, usually with vector extensions like SSE, or nowadays it's called AVX. But they also behave quite differently. So they might bitwise be very wide. So the largest AVX are, I think, up to a kilobit. But it's not like one number with a huge value range, but those extensions, they use vectors of numbers. So while the register to store this data is very large, it can only store individual numbers with a certain granularity, and then in parallel execute instructions on those numbers, which increases, of course, the throughput immensely, but at the same time is very rigid. So for just controlling what an application is doing, or writing some sort of server or something, this would be completely useless. It's great for encryption. It's great for a lot of media applications like audio and video codecs. You can use it for implementing AIs, or generally just implementing some neural networks, but of course dedicated hardware or a GPU is much more efficient for that, so you would not want to run it on a CPU. That would be, if it's super simple and very small, you can do it, but that would not be something advisable. So we will not be taking a look on those special types anytime soon. Yeah. Good. So let's proceed with this thing. So so maybe before we proceed with the next boring things, maybe we should take a look on something exciting. So as I have told you, we are using in C and C++ a lot of equations, and even such a simple assignment in principle is a very basic equation. So we can this is code which will be executed, so we can put a breakpoint, for example, on the char here, and when we run it, we can then see in the debugger how the code to put a 0 in memory actually looks. So one thing we noted, of course, in our main function is that there is quite some code here at the beginning, but this we will not care for right now. Here we are only interested in how this is implemented on a very low level. So as we certainly all know, a computer has memory, the RAM, which is huge and fast nowadays, but the CPU also has registers, and we can here in fact enable quite a few more of them. So the those basic registers we see here are just the ones available on x64, so the AMD 64 instruction set, which is a 64-bit version of the old Intel 32-bit instruction set architecture. But then we have some segment registers, we have floating point registers, so for the floating point numbers, and then we have flag for all these different vector extensions that have been added over the years, like MMX, SSE, then AVX, AVX512. I don't have, my CPU does not support anything bigger. The neon things here are for ARM, so ARM also, so ARM is a different architecture set. We can talk about a bit later about individual architecture sets, how they differ from each other. But they also have vector extensions, but since it's a different architecture, they are called differently, they behave differently, etc., etc. So, and here, of course, they are therefore disabled. There is this 3D Now that was something from AMD very long time ago, and it didn't catch on. So I guess if you are particularly unlucky, you might find some very old program you want to run which actually necessitates this, and then it won't run on a modern CPU. But since even back then those features were not everywhere, so they were only on AMD CPUs, usually such a program would check whether these instructions are available and then choose different code paths if they are not. So I guess you will not really find in a wild an application which would crash when this is not present. Yeah, and then we have flags. The last thing, which are different, often single bit flags inside the CPU indicating particular states. So let's quickly disable all those things that we don't need, at least not now. We will only keep CPU segment we also don't need. We will only keep the basic registers, the floating point registers, and maybe the flags. That might be interesting. The rest we don't need. And what is a register? Basically, it's a very small amount, tiny bit of memory, which is located inside the CPU, and the CPU foremost works on data stored in these registers. And if you want to do something with memory, with data from RAM, you need to load it into a register. On x86 or like on any other complex instruction set sort of architecture, this happens. This is implemented such that you can have instructions which take a memory address and then already do something with it and put the result only into a register, or that they take data from a register, do something with them, and then write them directly to memory. So it's like such an instruction, that's why it's called a complex instruction set, can be made up of multiple individual single steps, like load from memory, add a value, and save to register, or take from the register, multiply with a value, and store to memory. What you won't find are memory only instructions, so like that would just take an address, load it, do something with it, and then put it back. Those don't typically exist in instruction set architectures. I mean, one could make such an instruction set architecture for some FPGA, but then no one would be using it. So it's it would be just a purely academical. But this is like the most characteristic of complex instruction sets, that they are like this. They have this multi-step, multi-operation nature, and in fact, internally the CPU will be breaking up such one opcode into multiple individual micro opcodes, and then execute them one by one. And once it's done, then the execution will proceed to the next location, which, by the way, already allows us to demonstrate something. There is one of the registers, the instruction pointer here. It contains the memory address of the instruction which we are executing right now. So if we step to the next instruction in the debugger, we see that this value, this instruction pointer, got incremented by however many bytes the previous instruction was long. So this is how the CPU tracks what it is doing. It has this instruction pointer which points to memory, and this is the case for every core. So every core in your CPU has an own set of registers, an own instruction pointer, and the instruction pointer is being automatically updated as it executes code. At this point, you might wonder how this works. Since your computer has like thousands of threads running in parallel, but only 4 or 8 or however many cores you have instruction pointers. This is done with the help of the operating system. Basically, your operating system sets up a core to run for a certain defined amount of time. It sets up all the registers and then it makes it execute. And then the core does its stuff until an interrupt comes and tells it that it's done. The control goes back to operating system, and the operating system then can change the instruction pointer to the instruction pointer to a backed up copy of the instruction pointer of another thread, and do the same to all the other registers, since all the data need to be consistent. And then the execution resumes, and then the other thread does something, and this is switched billions times per second. And of course, the more switching you have, the slower everything becomes. So ideally, you would want to optimize your code to not create too many context switches, but this is something nowadays that is more or less out of your control. So the only rule here might be don't create unnecessarily many threads if you don't really need them. Those registers, especially the ones I hit before, the segment registers, they are, so not all of the registers that exist can be written by the application directly. So some of the registers are configured such that the CPU must be set to be in a privileged state to be able to change them. And this is basically how the operating system kernel isolates itself from the applications that are running. So the applications are just doing their thing, but they can only work with the memory which they have been given. They cannot change memory mappings. What this is we will learn later. They cannot change critical registers. They can only change some of the registers and the memory that they can access. And then when the control goes back to the operating system can then change any register at once. And this is how it switches the threads and to other things as mentioned. So let's continue here. So we have our registers, and since we are not doing any actual operations here, basically most things that we'll see here will not invoke registers, but some operations will. So let's quickly restart the application since we already had a step. So let's see how, for example, we would assign 0 to a char that lives somewhere in memory. Just maybe one more note. If you have a debug build, every of your variables will live in memory somewhere, and while it's worked on, a copy of it will be present in some of the registers. If you have a release build, the compiler might opt to not store the variable in memory at all. It will just exist in a register for all its lifetime, and once it's done, it's done. So this is a difference one should keep in mind between the release and debug builds. Okay, so here we want to assign 0 to our char. So we have an operation called move, which moves something somewhere, in this case a byte, and it takes a pointer, so a memory address where this byte lives, and then it takes an actual value like 0 and can write it directly to this memory. And we can switch a few things here. So we can disable symbol names. So we see that what really is written here is like move to RBP is a register. So basically we have a register and which points to some place in memory. To this value we want to add the number 4, and then to this gives us a new address increased by 4, and then at this address we want to write 0, and all this can be done in one instruction. There are, however, other instruction sets. So I already mentioned ARM CPUs, which I'm sure you are familiar with. All your phones and many tablets and a lot of pretty much all the embedded devices, everything uses ARM nowadays. And this is a rapid instruction set architecture, RISC, in comparison to what the normal desktop computer is, a CISC instruction set. And this rapid instruction set architecture is quite different from CISC in the sense that all the instructions are rather simple. So you don't have like complex instructions that do many steps, but at least generally, and especially you don't have instructions which can access memory and do something. You can have a dedicated instruction to load from memory to a register, or save from register to memory, and then you need another instruction that does something, then another instruction that does something, and so on. So it's much more simple in a way. And back in the days, people thought that this way computers will become faster, which didn't really work out. What can be done apparently this way is to save on energy costs, but the way modern CPUs are dissecting internally a complex instruction into simple instructions basically makes the difference between those two architectures with regard to the top performance that they can reach not really that large. So if you are constrained by an energy budget, ARM is much better. So for the laptops it's a great thing, but if you have some really powerful Threadripper workstation that doesn't care for the power consumption, it will not, you won't really see a big performance difference between such a system and a ARM system with regard to just the raw compute, if the wattage doesn't matter. If the wattage matters, then of course ARM is superior currently, although the newer Intel chips are also quite good. So um, basically just both concepts are asymptotically approaching some limit of what is feasible, and the differences are not that big as they were a long time ago. And if you are interested in ARM, we could maybe at some later point spin up a virtual machine on a ARM device remotely, and then see how this this assembly looks on ARM. But since of course doing everything double would take twice as much time, and we don't have that time, most things we'll just be doing here looking on x86 64 architecture. By the way, before we proceed with this, you can of course here switch to just 32-bit, so we can review the same code, how it would look on a old 32-bit Intel system, but we'll do this later. So as said, so we have here this move instruction, which already reads a value from a register, and this RBP, so basically BP is short for base pointer. All the registers in the 64-bit mode, the basic registers in the 64-bit mode are prefixed with the letter R. If you would be running in 32-bit mode, they would be prefixed with E. But the way the assembler and the instructions are set up is that you could use the shorter aliases to address the lower portion of a given register. So if you would write assembly, like we see here in the next line, for example. So let's continue. So here we had our assignment of 0 to a memory address, a place in memory. Here the next thing we do is we want to have a to assign 0 to a short, and the compiler here decided to do it quite differently. It uses a register EX, which basically is the register REX, but since it's EX, it's just 32-bit, even though we actually are only interested in 16-bit, which we'll see in a second how this works. And what it does is it just XORs, it makes the exclusive OR operation of the register with itself, and the way XOR is defined, no matter what was in the register before, the result will be 0. And since the instruction can be encoded in only 2 bits, apparently the compiler chose that this is the most efficient way, or at least the close to most efficient way for a debug build to do this. The other option would of course might be to just load a value from a known address or something, but this would yield a bigger code or a less efficient code, and thus when you are browsing disassembled code, you will sometimes see such strange constructions, even though this is just a simple is equals 0. So it XORs. So now we know that this register, so currently it actually contains 1. So if we execute this instruction, single step, as you see, it became all zeros. Also a note here, the way this works is that whenever something changes, be that in memory, actually we could go to RBP to see it, or in the registers, the change from previous step to next step is highlighted in red, so it's quite nice. Okay, and the next thing that here what will be done is it again uses the move instruction, but instead of having the value encoded inside the move instruction, it just takes a register, and here it takes the register AX, and AX is like the lower portion of RAX. So the registers allow this sort of segmented access that you can they're like made up of smaller and smaller pieces, which are kind of corresponding to the older and older versions of the instruction set architecture. So if you get an extremely old CPU that only could run DOS, then it would be a 16-bit CPU, and it would have only the AX and register, and would not have the EAX. The EAX is already the extended version of it. So here, by this semantic, it just takes the lower 2 bytes of the 4-byte number and copies them into the address. So we could actually watch here if we see this change happening. We make a single step, and we see here. So the other value apparently already was 0, so we didn't need to do anything. But it changed, so it only highlighted what it really changed. but as said before, the values before the initialization are unknown, so they can contain whatever. Okay, so this is this, and then of course let's see the next instruction. Then we want to assign 64-bit, sorry, a 32-bit number, which then we do again the same way we did here with a move. Just that you notice that this move is much longer, and depending on how how the instructions are encoded, you might, for example, only have the option between moving one char somewhere in or moving 32 bits somewhere in. Apparently here we did not have the option to move in just 16-bit number, and this one is longer by 3 bytes, but this is only 2 bytes, so kind of using these two instructions saved us 1 byte of code, which in the DOS era was quite important because you had very little memory. Nowadays the compilers are just made to automatically optimize. We don't do such things by hand anymore, but it still, of course, is still good to try to minimize the amount of code. For example, one of the things which is the biggest bottleneck with ARM architecture is the memory bandwidth. Since here, as you can see, you have just a few bytes and you already crammed in quite a lot of instructions into it, quite a lot of payload. On the ARM, you would need to read, in this case, at least 2 32-bit instructions, so this would already be twice as much memory bandwidth needed. So first of all, on the ARM, I said what you want is as much memory bandwidth as you can, and secondly, what we learned for our own use case is that if we can reduce the amount of memory bandwidth needed, that will be an improvement in either case. And so this is why the compiler sometimes does such tricks. Okay, so let's just proceed with this operation. Again, we set a few zeros somewhere where some of the data were not quite yet initialized. The next thing, of course, what we want to do is to set the 64-bit integer, which interestingly enough we can use pretty much the almost same instruction as we have here. It's very similar. Just it's prefixed with a certain prefix, and this is how this 64-bit instruction set has been designed. So Intel a long time ago tried to make a completely new 64-bit instruction set called Itanium, and so that was a mark brand name for the CPUs, and that was or Itanic. And they people make jokes that it's well, Itanic, like the Titanic, because it's no one wanted to buy it except for HP, because they did some assumptions that were not true realistically in their design, plus the way this code executed 32-bit code was extraordinarily inefficient, so you could not run all software with any sort of decent performance, which was more or less the killer for that project. AMD learned from that, and when they invented their own 32-bit instruction set, they just took the existing 32-bit instruction set, increased the width of the registers, added 8 more extra registers, and kept most of the same instructions just by adding a few prefixes. So 32-bit code runs on a 64-bit machine just as fast as it would run on a dedicated 32-bit machine, while you can, of course, at any point switch to 64-bit once you update your software. So this compatibility was the reason why this architecture was so successful, and you see it in the disassembly very often that really you just change by adding a handful of prefixes. And interestingly enough, most of the instructions which handle numbers, like adding, subtracting numbers, etc., they only have versions like this which are 32-bit. So you kind of would need a bit more code if you would want to do some math on predefined 64-bit numbers, for example. But realistically, you never do that. If you hard code something, then the compiler can do it and just put the result into your binary. And if you are calculating with some variables, usually it will be enough to have shorter numbers. So the only instruction of which there actually is a 64-bit version to put a 64-bit number into a register is this move instruction, so that you can initialize large values with one instruction, but all the others expect that you will not be really doing this. And then of course if we continue, we see more or less the same tricks used to initialize our unsigned variables. And this is already one interesting thing that we can notice here, that the CPU as such does not really care whether the numbers are signed or unsigned with regard to the place where they are stored. It's just memory. Everything is just memory. And how the memory, whether a variable is signed or unsigned, what this defines is for the compiler which opcodes then to use when touching this memory. And of course an assignment is the same whether it's signed or unsigned, so the compiler uses the exact same opcodes. If we would switch to something like addition, subtraction, etc., do something later, then depending on whether the variable is an signed or an unsigned integer, we would end up using different instructions in the disassembly here. And then of course last thing here with regard to our floating point numbers, here we assign them and we use the same trick as here with XOR and the move, but of course the operations are called differently because they are using this MMX registers which are used for floating point numbers. So did I hit them? Yeah, let's keep them. Okay, so let's just execute them. Let's tap until there. Click. It was already 0, so this will be boring, and then it saves it to memory somewhere. The other one would do the same. It would set it to 0. Unfortunately, we don't see anything if it doesn't really change anything. So, of course, since it's using different registers, you need special instructions if you want to move data between. So we will later, once we try to write some equations with, I guess during the next lecture, because this time is already running out, then we will see that there are special instructions to convert values from integer to float and from float to integer, and then only once. And the way they are working is they are not just converting the data, they are copying them to a different type of register. So a normal instruction that does floating point cannot operate on a integer register and vice versa. The data need to be moved. Okay. So so much to this. We will of course in the later lectures take much more looks in all these different assembly things, but don't be worried, there is nothing with regard to this assembler that would be part of a homework assignment. So all those things are important to understand, to get a deep understanding on how C and C++ really works under the hood, but it's not something that you need to be able to repeat yourself. It's just as a understanding aid intended, and not as something that you need to master. Yeah. Okay, so let's continue. Next thing you might be interested in is of course how to, so since we are still at the level of assigning values, and we have already seen here like just decimal numbers, hexadecimal numbers, so if there are any other ways to assign a fixed value to a variable. So generally such things are called literals, because they literally are assigning a fixed value. What we also can do, as with regard to prefix, we can use a const prefix. The const prefix kind of says that this variable, once it has been assigned a value, will keep this value forever. But this is not something that would in any shape or form change the code that the compiler generates. The only thing that const does is that if you try to assign to a const variable later in your code, the compiler will just throw an error and not want to compile it. Which also means that since this const variable should usually live somewhere in memory, if you override this memory, you will change the value of the const variable, and there is no mechanism in the CPU that would guard this variable from being changed. There are mechanisms how pages of memory. A page is a block of typically 4 kilobyte. In modern systems, modern ARM systems, on x86 is not the case, pages can be 16 kilobyte in size. And what you can basically do with pages is you can set different protections. So for example, you can say that a page is read-only, but you cannot do such things with the granularity of let's say a single variable. So if you would have a lot of const variables and a compiler which is smart enough, it could be made such that it would put all those constant values into a read-only page of memory. But usually this is not something that that is done, because you have usually const variables sprinkled around your non-const variables, and you not necessarily always want them to be moved somewhere. Also, an important thing to know is that you can use const variables for things where the compiler will take the value at compile time and apply it to whatever it does at compile time. Thus, if you would change, if this variable would even survive the compilation step and be then present in memory, if you would change this memory, it would not necessarily propagate to all places where this variable have been used, because the compiler at some place might have said, okay, this is a const variable, I know it's 5, for example, and here I'm supposed to add this to some other variable, but this variable is already in memory, so I would need 2 operations, but then since I know it's 5, I can just use 1 operation and save on operation. So the long story short, don't try to modify const variables with dirty hex, because this might turn out very bad. So, but let's use it. So we just prefix const to int or to unsigned int to tell the compiler it's const. My var that's decimal. Of course, this we already had 1, 2, 3. Then of course hexadecimal hex 0x7 7b would be the equivalent of 1, 2, 3, and the compiler even tells sorry, the IDE even tells us this. So if we move it, it shows us the value in decimal. There is, by the way, somewhere a switch here, not here, not here either. I usually switch this once and then it's there forever. I don't remember it. There is a switch which you can switch so that it will show you hexadecimal values instead. Well, if you want that, you can look for it later. That should be with the debug tools. Yeah, we don't see the debug tools here. We enable debug tools. Here it is. So if we press hex, then it will show us. Okay, here it doesn't work. In some places it will show then in hex. Apparently in this tooltip it always uses decimal, but in other places it will show hex. Okay, what other notations we have? Well, we can use binary notation, something that is very close to how a CPU internally sees all the values, and binary is 0b. So like hex is 0x, binary is 0b, and then you use the ones and zeros. So we have 0, 1, 2, 3, 4, 0. This should be 1, 2, 3, I think. Yes. And there is yet another notation which no one uses in this century, in this millennium even. But for some reason it is part of the C++ specification. It's called the octal notation, and you kind of prefix a number with a 0 and then just write numbers 1, 7, 3. And octal notation means that you can only use values 0 through 7. You cannot use larger numbers. So like hexadecimal is 0 through f, decimal is 0 through 9, and then octal is just 0 through 7. Or was it 0 through 8? No, I think it's 0 through 7, because the next one, like the number 8 would be already once more like 10. So this thing still evaluates 1, 2, 3. And the thing is that it starts with a 0, so someone might think that that looks nicer, but this changes the actual notation. Now it's just 83, so it's not what we want. So it's important to know that do not prefix your numbers with 0, because that changes their meaning entirely. Okay, there are some other ways to provide a value, which is quite wants a type, of course, char in this case. So obviously, when writing code, you would want to write some messages or some text, and how to do that we will learn later. But with regard to single characters, you can use the single brackets and then put a character inside, and this character in fact is 1, 2, 3, the opening curly bracket. And in principle, you could of course assign a char also as a with a hex number, so you could just write my char is equals then the hex number. This would be also a completely valid thing. There is, however, yet another way how you can assign chars. You can use an escape sequence \x 7b. It's again the same value. Let's just add the underscore so that it's not the same thing. And the reason why this exists is because, for example, how would you specify the char of this is too smart. So if you would just want the char single quotation mark, if the single quotation mark already has a meaning. So the idea is that if you prefix something with a backslash, it loses its special meaning, whatever its special meaning might be. So if you are writing a string in double quotation marks, you can just write a single quotation mark with a backslash. Which brings us, of course, to a problem. How do you write a backslash? You write a backslash by writing 2 backslashes, because the first backslash takes the special property of a backslash away from the following backslash, and so on. But we'll take a look on these escape sequences in more detail later when we learn how strings in C are represented. As you might have noticed here, there are no registers in the CPU that could hold a string of any meaningful length. So just to say something that will come in the later lectures, a string in a low-level representation basically is a memory location which contains an array of characters. And what an array is, again, is something that we'll learn in one of the later lectures. Here we are really starting with the very basics. So that's that. To be able to assign values. There is one more thing that one should maybe think about or know about. It's an enum. This basically is a way to define it's a way to define values, to give names to values. My enum 0 is equals 0. My enum 1 is equals 1, let's say. And the nice thing is that if you continue, it will automatically increment the last value it saw. But you can like introduce like my enum 10 is equals 10, then it will continue from this further. And this enum kind of acts like an own data type. So you can just write enum my enum, and assign to it one of those values. We should have a 1, 2, 3, 1, 2, 3, because we use 1, 2, 3 so often. And this is kind of just a placeholder. So the CPU is completely unaware of this. It just tells the compiler that we can use some string which conforms only to the normal naming convention in C instead of the number. So this is quite a nice mechanism. And I see we are already kind of almost running out of time. So I will just paste a little text here and quickly explain it. So just so that we can recap all the different notations that we have. Hexadecimal, binary, octal, and decimal for a set of values. In this case, the values are so chosen that in the binary notation they always are represented by 1-bit set. And the other thing I should mention is here maybe, or let's do it also here, the binary representation. So here an example of numbers 0 through 16. So in the hexadecimal notation, 0 through f. So f is like 15, and the next one is like 1 over in positive values and negative values. So we see that kind of the lowest positive value is 0 and the lowest negative value is -1, kind of. So this is like symmetric, and then we are just counting the ones, like 1 is 1, 2 is 1 further over, 3 is both ones, and so on and so on. And of course with negative values it's the exact same thing, just that shifted by 1, and that we are inserting and counting through zeros instead of ones. And this signed and unsigned can often be also, you can think of it that if you have a signed value, then if the highest order bit is 1, then the value is negative, and if the highest order bit is 0, then the value is positive. While of course for unsigned numbers, it's just positive values all the way. Okay, so that's that. Any questions? There is no script. There is the recording, and I will upload all these projects maybe with a few more comments to the Moodle. So this should be as good as a script, I would say. Especially with all the comments, the examples that you will see are reasonably self-explanatory. Any more questions? No, that's it. No more questions?
I just wanted to ask for a colleague who he left a bit early,
Yes?
and he was asking if it's okay and if it's if presence is mandatory. Yeah.
I already mentioned that presence is not mandatory, but it's encouraged. So you should be here, but if you cannot be, then just watch the recording on YouTube.
Okay, sorry. Thanks.
Any more questions? Okay. So if there are no more questions, then let's finish here for today. In the next lecture, we will finally start doing more interesting things. So some equations, and see how this works in C and C++, what sort of operations we have, etc. And then we'll see where we come from there. The over next lecture will be, I guess, flow control, so ifs, and at some point we'll arrive at functions that will be particularly interesting. Yeah, so have a nice evening. We'll see each other, I think, next week. Bye bye.
Bye.